Welcome to AI Paper Slop.
Hey, everyone.
So imagine spinning up a tiny 3 billion activated parameter model and just watching it completely dismantle a trillion parameter giant on complex math and coding benchmarks.
Yeah, it's wild.
No massive pre-training scaling, just pure hyper-aggressive post-training. Today we are looking at the Mach-Mind-4-Flash technical report published by Liauto Inc.
Right, and for those of you out there building and deploying foundation models, this paper is a massive wake-up call regarding what is actually possible when you optimize your post-training pipeline.
Exactly. So here's your rapid-fire summary to get us started. Mach-Mind-4-Flash is a 35 billion parameter mixture of experts model, but it only uses 3 billion activated parameters during inference.
Just 3 billion.
Right. And through pure post-training optimization, so no extra pre-training, it matches or outright beats 100 billion to 1 trillion parameter model.
Models like Quinn 3.5, 122B, or even Kimi K 2.5.
Yeah. And the secret sauce here is a 3-stage pipeline. First, they built a unified reinforcement learning and on-policy distillation infrastructure.
The plumbing, basically.
Right. Second, a multi-teacher on-policy distillation method, they call it MOPD, that fuses domain experts without that notorious capability Seesaw degradation.
Which is huge.
And third, a novel token efficiency method called HMPO to essentially cure the overthinking problem that plagues modern chain-of-thought models.
Okay.
Let's unpack this.
Let's do it.
Because, you cannot train massive specialized experts at scale without the hardware and infrastructure to actually support them.
You really can't. If you're provisioning GPU clusters, you already know that keeping throughput high on a MoE architecture is an absolute nightmare.
Oh, totally. So the foundation here is their unified RL and OPD framework.
Right. So if you've ever tried to run knowledge distillation and reinforcement learning simultaneously, they usually sit in two completely isolated pipelines.
Yeah, you have distillation code base and then a separate RL code base.
Exactly. And trying to synchronize the data loaders and the model weights between those two distinct pipelines is just a scheduling disaster.
It's awful.
So Liauto bypassed this entirely. They fused them into a single joint training paradigm under a unified weighted loss function.
So the total loss simply equals alpha times the OPD loss plus beta times the RL loss, right?
Spot on. The elegant part is how you control it. If you set alpha to 0 and keep beta positive, the distillation path just shuts off.
So the infrastructure just acts as a pure standard RL environment.
Exactly. And if you flip it positive alpha, 0 beta, you get pure online distillation, where the model relies entirely on matching the teacher's target distribution.
Which you typically use for the capability initialization phase, right? Because it offers that incredible gradient stability early on.
Yeah, that's right. But what's truly fascinating is when both alpha and beta are positive, you have two optimization paths running mutually independently, but superimposed on the exact same infrastructure.
Right, so the distributed scheduling, the experience sampling from VLLM, the asynchronous reward routing is all happening under one roof.
Which saves massive overhead.
But wait, combining all that creates a severe compute bottleneck, especially because they are dealing with a mixture of experts architecture.
Oh, massively.
Like routing tokens to different experts across hundreds of GPUs just destroys global memory bandwidth. To make this unified roof actually hold up, they had to dive deep into operator-level acceleration, didn't they?
Yeah, they had to go right down to the metal. They integrated a framework called Sonic MO directly into the Megatron core backend.
And they deeply leveraged the specific hardware features of NVIDIA's Hopper GPUs to do this.
Right. When you are writing CUDA kernels for MoE, the traditional approach requires a token permutation step.
Which is super slow.
Yeah, you literally have to physically sort and move tokens in memory based on which expert they are routed to before you can actually do the matrix multiplication.
And that permutation step just absolutely throttles your global memory access latency.
It's a killer. So Liauto implemented an indexed grouped GM operator. Instead of moving the data, this operator just uses pointers.
Wow.
Yeah, it calculates the matrix multiplication by directly indexing into the unsorted token memory using the Hopper Tensor Memory Accelerator, or TMA.
Which skips the permutation overhead entirely. You're just pointing the computation to where the token already lives in memory.
Exactly.
And the way they handle the shared experts is just as elegant. In a standard setup, calculating the shared expert creates a massive communication roadblock because Every GPU needs a piece of it.
They solve that with what they call a segmented shared expert fusion strategy.
Right.
They took that monolithic shared expert computation and physically fractured it into 3 distinct stages: the all-gather communication, the actual expert computation, and then the reduced scatter communication.
And by splitting it up like that, they could use multiple CUDA streams to overlap these stages with the standard expert parallelism computation happening on the other experts.
Yeah, it's a classic latency hiding technique. While the GPU is doing the math for the standard expert, the network interface is concurrently doing the all-gather for the shared expert.
So you aren't just sitting idle waiting for tensors to cross the NVLink.
Exactly. End-to-end, this specific architectural tweak delivered a 17% training speedup on the Qwen 3.535B model.
Which is wild. I mean, for anyone out there paying cloud compute bills, a 17% reduction in training time on a 35 billion parameter model is literally hundreds of thousands of dollars saved.
Oh, easily. And the whole infrastructure is completely modular. When you want to add a new domain teacher to supervise your student model, you don't rewrite the pipeline.
It's basically like a plug-and-play motherboard for AI training.
That's a great way to put it, actually.
You just attach a routing identifier to your incoming data batch. The underlying Ray cluster detects that new identifier and automatically provisions and spins up the new teacher's nodes.
Right. It handles the tensor parallelism scale, allocates the GPUs asynchronously, and the student model's core training logic doesn't even know it happened.
It just seamlessly starts receiving distillation gradients from a new node.
Exactly. But, building this god-tier infrastructure is completely useless if you feed it conflicting signals.
Right, the seesaw effect.
Yeah. If you've ever tried to force a single base model to optimize for creative writing, Python coding, and calculus all in the same batch, you have seen the capability Seesaw.
Oh, I hate that. The model figures out how to write a beautiful Python script, but suddenly starts formatting its creative writing as code blocks. Or it completely forgets how to do basic arithmetic.
Yeah, it's brutal. Which brings us to the core training philosophy of the Mach-Mind paper. Specialization, then integration.
Right.
They completely isolated the domains during the initial reinforcement learning phase. They didn't mix the rewards at all.
So they spun up distinct parallel tracks.
Right. A reasoning track for math and STEM, a general track for instruction following and safety, and an agent track.
Let's focus on the reasoning track first, because if you are designing reward functions, reasoning domains are notoriously unforgiving.
So unforgiving. The outcome signals are incredibly sparse.
Right. If you ask a model to solve a complex topology proof, the final answer is a binary state. It's either completely right or completely wrong.
Exactly. But the logical path to reach that answer might be like 1,000 tokens long.
And if your reward function only issues points for the final correct answer, a nascent model will just never randomly stumble upon the correct sequence of 1,000
It
tokens.
just gets stuck in a zero reward trap and the gradients completely die.
But wait, if you try to fix that by using a dense process reward in stage 1, where you give the model partial credit for intermediate reasoning steps, like setting up the equation correctly, doesn't that just invite catastrophic reward hacking?
Oh, 100%.
Like the model will quickly figure out that it can maximize its score by continuously generating intermediate steps that just look structurally correct, triggering the process reward repeatedly without ever actually attempting to solve the broader problem.
It absolutely will do that, and that is the fundamental tension in reasoning RL. But Li Auto's two-stage reward curriculum addresses this so elegantly.
Okay, how so?
Well, they acknowledge that dense process rewards inevitably lead to hacking, so they strictly quarantine the process reward to stage 1.
Yeah.
They use it purely as a bootstrap mechanism to pull the model out of the zero reward trap and stabilize the cold start, but they monitor the validation metrics incredibly closely.
So the exact moment the model's accuracy crosses a predefined capability threshold, they just mercilessly cut off the process reward.
Exactly. Stage 2 transitions to a strict outcome-only reward.
Which forces the model to internalize end-to-end correctness.
Right. If that final answer is wrong in stage 2, the reward is absolute zero. It doesn't matter how beautiful or mathematically sound the intermediate steps looked.
So the reward hacking stops instantly because the exploit just no longer yields a return.
Exactly. And they pair this curriculum with a very aggressive, difficulty-based pruning technique.
Oh, I love this part.
Yeah, they take their base supervised fine-tuning model, the SFT model, and force it to run inference on the entire training dataset 8 separate times. If the SFT model gets a specific question right 8 out of 8 times, they just delete that question from the RL training pool.
Which, from an information theory standpoint, makes perfect sense. If the model already knows the answer with 100% confidence, the gradient generated by training on it is effectively zero. It's just wasted compute.
Spot on. And on the flip side, if the model gets it wrong 0 out of 8 times, they also toss it.
Because the problem is too far beyond the model's current latent space, right? It just acts as statistical noise.
Exactly. So they only run reinforcement learning on the Goldilocks questions, the ones where the model gets it right maybe 3 or 4 times out of 8.
Because that's where the learning signal is actually dense and actionable.
Right. And that handles static reasoning brilliantly. But, mathematical proofs are static environments. The real world isn't.
Very true. When your model needs to execute code, search a file system, or navigate the web, static rewards break down completely. You have to train agents for long-horizon, multi-turn tasks.
And that brings us to their agent RL tracks, and specifically end scaling. You cannot just train an agent on static traces of API calls.
Right, because if the agent makes a slight error in turn 3, a static dataset can't tell it how the environment would have naturally responded to that specific error.
Exactly. A robust agent has to inspect dynamic states, it has to recover from hallucinations, and recognize completion states organically. So LiAuto scaled the environments themselves.
They deployed 3 distinct environmental families during training, right?
Yeah. First, actual file system execution environments. These are real, sandboxed Linux workspaces where the agent is running live shell commands, manipulating files, and observing raw standard out errors.
Second, they used programmatically verifiable Python environments with deterministic state transitions.
Right. And third, model-simulated environments for open-ended, non-deterministic interactions.
And for those of you building agentic workflows right now, pay close attention to how they handled the code agent. They completely abandoned JSON for their tool call formatting and built an XML-based template instead.
Yeah, which is fascinating. JSON might be the industry standard for APIs, but for an LLM generating long horizon trajectories, JSON serialization introduces a massive vulnerability.
Oh, completely. JSON relies on highly nested brackets and aggressive character escaping.
Right. If your agent is 15 turns deep into a complex task and hallucinates a single rogue quotation mark, or forgets to escape a backslash inside a nested string, the entire parsing tree just shatters.
The environment throws a fatal syntax error and the trajectory dies.
Exactly. XML, however, naturally supports flat string representations. It has substantially lower syntactic overhead.
You just open a tag, dump the raw text or code, and close the tag.
It is significantly more resilient to the minor formatting hallucinations that plague LLMs during continuous tool use.
They also implemented rule-based error masking during this training phase, which I found super clever.
Yeah. Normally, if an agent writes a broken Python script, you might be tempted to penalize it and just truncate the sequence.
Right. But here, they retain the erroneous action inside the context window, so the model can physically observe its own failure. But they mask those specific error tokens from the lost computation.
So the model isn't penalized for exploring and failing. It's trained on the subsequent tokens where it reads the error log and writes the patch. It actually learns the mechanics of error recovery,
which creates a highly resilient agent. Now, for the web searching capabilities, they spun up a dedicated deep search RL track designed specifically for multi-hop open domain retrieval QA.
Right, they built a dual pipeline synthesis engine for the training data. Pipeline A constructs a Wikipedia-directed acyclic graph, or DAG.
Which is, think of a DAG like a massive subway map where the stations are Wikipedia entities and the tracks are the intra-article hyperlinks.
Right. By navigating this graph, the researchers can mathematically guarantee the exact number of logical hops required to connect two disparate concepts.
So if the answer requires traversing 4 physical edges on the graph, the model must execute a 4-hop reasoning chain.
Exactly. And then Pipeline B deploys a React agent to explore the broader non-Wikipedia web in real time. It actively searches for cross-domain entities linked by what they term an attribute coincidence edge.
And the training query is then synthesized, so the final answer exists only at the precise intersection of those 2 independent knowledge chains.
It forces the model to synthesize disparate information sources dynamically, rather than just relying on memorized parametric knowledge. But this introduces a massive engineering challenge regarding context windows.
Right. But I mean, if your model wanders down a web search rabbit hole for like 40 turns, pulling in raw HTML and search snippets at every step, how does it avoid context overflow without just blindly truncating?
Because if you truncate, you hit the 128K context limit rapidly, and the model instantly suffers from amnesia.
It forgets the original prompt and the tools it already tried.
Exactly. So LiAuto implemented context restart via progress summary. It is conceptually similar to a video game save state.
Oh, that's a good way to look at it.
Yeah, instead of letting the raw HTML and search logs endlessly bloat the context window, the framework actively monitors token capacity. Right before it overflows, the system pauses the generation.
Okay.
It prompts the model to compress its entire trajectory into a highly structured, dense progress summary. You know, what it knows, what failed, and what the immediate next step is.
The framework then flushes the context window entirely and restarts the environment using only that dense summary as the new initial state.
Exactly. The agent maintains its logical progress without dragging the dead weight of 40 turns of raw search history.
Okay, so let's look at where we are in the pipeline. We have a lab full of savants in isolated rooms. We have a math genius, a coding expert, a deep search specialist, and a safety module.
Right.
But if we try to merge them back into a single 35 billion parameter brain using standard RL, we trigger that capability Seesaw. The math gradients destroy the creative writing weights.
Yep.
So how does Mach-Mind-4-Flash fuse them losslessly?
They utilize multi-teacher on-policy distillation, or MOPD. Standard PPO tries to push the model's weights toward a moving target of higher rewards, which often averages out and destructive interferes across different domains. MOPD, instead, uses a routed reverse KL objective.
Remember the plug-and-play architecture we talked about earlier?
Right. The student model generates its own rollouts. Each training sample carries a routing key that dispatches that specific sample to the frozen domain expert, the teacher that mastered that exact domain.
The student then minimizes the token-level reverse KL divergence against that teacher's probability distribution. And the choice of reverse KL here is critical for you to understand, right?
Very critical. Forward KL is mean-seeking. It tries to cover all the possible modes of the teacher, which can lead to the student generating blurry, averaged-out garbage when trying to satisfy multiple domains.
But reverse KL is mode-seeking.
Exactly. It actively penalizes the student for generating tokens that the teacher considers low probability. It forces the student to carve a very precise, narrow path that strictly aligns with the expert's highest confidence logic.
So it prevents the seesaw by forcing strict adherence to specific expert behaviors.
Yes, but calculating exact reverse KL across a 100,000 token vocabulary for every step is computationally impossible at this scale.
Right.
To make it viable, they deployed a single sample K1 estimator. The frozen teacher doesn't need to materialize and return a massive full vocabulary distribution.
It only needs to evaluate the specific tokens the student actually sampled and return a single log probability scalar per token,
which drastically reduces the memory bandwidth required for distillation.
But because the student's rollouts are generated asynchronously on a VLLM inference engine, by the time those rollouts make it to the training engine and the gradient step is calculated, the student model's weights have already updated a few dozen times.
Right. The rollout data is stale. It's off policy.
And this rollout of training drift will normally cause massive gradient explosions, right?
It will. To correct it, LiAuto applies a clipped policy gradient surrogate. It is mathematically very similar to how PPO clips its advantage estimates.
So it essentially attenuates the gradient for any token where the training engine's current probability distribution has drifted too far from the inference engine's historical distribution.
Exactly. It acts as a shock absorber for the loss landscape, and the resulting fusion is phenomenal. The student perfectly retained both general and reasoning capabilities without interference.
They even documented positive cross-domain transfer, didn't they?
Yeah, they did. When they ran ablation studies, they found that distilling purely from the code teacher actively improved the student model's mathematical reasoning and behavioral safety metrics.
Even when there was zero math-specific supervision in that batch.
Exactly. The rigorous logic of code formulation generalized across the latent space.
This raises an important question about compute efficiency, though. And here's where it gets really interesting.
Yeah.
During this MOPD distillation stage, they deliberately capped the student's response lengths to just 8,000 tokens.
Yeah.
They call it early stopping rollout.
Right. Even for incredibly complex math proofs, sprawling code-based generations, and deep search tasks that typically demand 20,000 tokens to resolve, the framework just brutally chopped the rollout at 8K.
Which saved massive amounts of VRAM and training compute.
Massive amounts.
Yeah.
Yet the final model still matched or exceeded the benchmark performance of training runs that utilized unlimited token budgets.
It proves that you don't need to force a model to memorize endless rambling traces to successfully transfer the core logical capabilities from teacher to student.
Which perfectly sets up their final post-training hurdle. The MOPD fused model is brilliant, but because it has internalized all this deep reasoning, it inherited a fatal flaw common to almost all strong chain-of-thought models today.
It severely overthinks.
It overthinks. It produces incredibly verbose, rambling reasoning chains that waste your inference compute and inflate your API serving costs, even for trivial tasks.
Right, if a user asks a deployed model what 2 plus 2 is, it shouldn't generate a 3-page chain-of-thought dissertation on set theory before outputting 4. How do you force a model to compress its reasoning without damaging its underlying intelligence?
They solved this with a single-stage RL method called HMPO, Hybrid Median Length Policy Optimization.
Okay, break that down.
Well, if you try to control verbosity using rigid manual token budgets, the model fails on complex tasks because a MART topology question legitimately requires more tokens than basic arithmetic.
Right.
So HMPO calculates an adaptive budget dynamically. For any given training query, the policy samples a group of different rollouts. It evaluates them and then calculates the median token length of only the correct rollouts in that specific group.
And that median value then becomes the mathematical boundary for a smooth cosine decay token reward. But wait, let me push back on the mechanics of that.
Sure.
If your loss function actively dispenses rewards for shorter sequences, won't the model rapidly realize the most efficient way to maximize its gradient is to just output the number 42 without showing any reasoning at all? It's the ultimate reward hack.
If the rewards were additive, yes, it would instantly hack the system. But the researchers structured the reward as a multiplicative composition. The final reward given to the model is the accuracy reward multiplied by the token length reward.
So if the model shortcuts the reasoning and outputs a wrong answer, the accuracy reward is exactly 0.
Exactly. 0 multiplied by a massive brevity reward is still mathematically 0. The short but incorrect trajectory receives absolutely 0 gradient update.
It creates a self-enforcing hierarchy. Correctness is an absolute prerequisite.
Right. Only trajectories that are both functionally correct and shorter than the median length of their peers receive the efficiency gradient.
And because that median boundary is dynamically calculated per query for every batch, it acts as a self-tightening curriculum.
Exactly. As the model learns to be more concise, the median length of the correct answers naturally drops, which continually pushes the model to optimize its reasoning pathways further.
The efficiency gains are massive. HMPO compressed the model's reasoning chains by 19 to 46% across the board, with a maximum accuracy drop of only 0.7 percentage points.
And the fascinating part, they only trained HMPO on the mathematics dataset.
Really?
Yeah, but because the model learned a generalized policy of answer as concisely as correctness allows, the brevity transferred 0 shot across the code, science, and instruction following domains.
That is incredible. Let's summarize exactly what this 3-stage pipeline achieved for the final Mach-Mind-4-Flash model. On the AM 2026 math benchmark, it scored a 92.70.
Huge.
On the behavioral safety bench, it scored an 80.74, which beat trillion-parameter models by nearly 13 full points.
Yeah.
It achieved frontier-level code generation and tool-use metrics. And it accomplished all of this utilizing a footprint of just 3 billion activated parameters during inference.
The cost efficiency of serving this model in a production environment is just staggering.
So true.
If we connect this to the bigger picture, the entire AI industry right now is completely obsessed with scaling inference time compute.
Right. The prevailing narrative is that to get smarter models, you have to throw more tokens at the problem at runtime, letting models spin their wheels and just think longer and longer.
Yeah, but Mach-Mind-4-Flash proves a fundamentally different paradigm. It proves that hyper-intelligent post-training utilizing mechanisms like MOPD for lossless expert fusion and HMPO for aggressive token efficiency can force a tiny, sparse architecture to reach that exact same frontier performance.
It fundamentally reshapes the Pareto frontier of accuracy versus token cost.
It really does.
So what does this all mean for you as an engineer? It forces a very uncomfortable examination of our current deployment strategies. Are we defaulting to massive brute force models in production simply because we lack the engineering discipline to build hyper-optimized post-training pipelines?
It's a tough question to answer.
When a 3 billion active parameter model can match a trillion parameter giant just by structuring its RL, distillation, and reward scaling properly, you have to ask yourself, does the future really belong to the biggest models or to the most elegantly refined? Think about that the next time you spin up an H100 cluster just to parse a few lines of code. Thanks for tuning into this deep dive.